You are listening to N is for Networking. I am Ethan Banks along with Holly Metlitsky, and today we are breaking down the different shapes and sizes that a network comes in. And by that I mean topologies, Holly. Topologies. Is that word, I don't know, it's sort of a technical word, topology, or I don't know, like a jargony sort of word. What does topologies mean to you?
It's funny because a topology to me is just a topology, but I would say it's some sort of map, maybe another word to use it, or a diagram, how things interconnect.
Mm-hmm.
I don't know how you explain topology without using the word topology.
Well, right. Well, my point in this, what I wanted us to talk about was the different common topologies, or I guess I chose shapes and sizes as like a trying to de-jargonize the word topology, network topology, into something that that's more accessible to everybody. But yeah, it's the way a network interconnects. And there's a lot of structure and specific topologies that networks frequently come in because you're trying to get a certain characteristic, a certain packet delivery characteristic out of the network. You connect all the pieces and parts together in a very specific way to get a specific kind of result. And that's really what we're getting at here. And over the years, a lot of different network topologies, network designs, if you will, have come into existence to meet certain goals that are kind of like, yeah, we tried this, we tried that, we tried the other, and we ended up here. This is a pretty good way to put a network together to deliver a certain kind of result.
Yeah, and I think what's interesting for me specifically about this conversation is initially all of these things look really similar. You think when we get into it, you'll see, but without knowing maybe the context or the reason for a specific topology in a specific use case, you're like, well, it's got 3 tiers or 3 hierarchies, or, that sounds all the same to me. Why are we calling them different things? So I'm excited to dive into that.
Okay. Yeah, because, well, before we hit the record button, you were like, why is leaf spine in a hierarchical design with access aggregation and core? Why are those different things? Aren't they the same thing? They are similar on paper, but no, they are in fact distinct. There's some distinct features to each of them with some different goals in mind. Okay, let's start with the very basic one, Holly, is the flat network. And if you describe an enterprise LAN as flat, what does that mean to you?
So if it's flat, it's got no hierarchy or layers or levels. So everything is working on the same base. So nothing is above or below, similar to how you would describe a flat network as like an organizational network. It's the same idea.
Yeah, and very small networks might be a flat network. I would also say a flat network typically doesn't have any routing except maybe at the very edge, like to connect to the internet or something. So like a small business might have a couple of switches and some wireless access points that are all backhauled to a firewall that connects them to the internet via some kind of a ISP provided modem, something like that. It's a flat network. It's probably got one, or it should have one block of IP addresses that everybody's working off of. It could be something as very simple like 192.168. Whatever, and that is fine for their whole network. And it's just a small, simple, flat network. Now, what can happen with a flat network is the business starts to grow, but no one who knows much of anything about network design was involved as that business grew. It's like, oh, we need more IP addresses. And they just add a different block of IP addresses, but they actually live in the same VLAN. So going back to some of our earlier shows, we were talking about how a different IP block would be in a different VLAN typically, right? So if you start out with 192.168.1 and it's a /24 network, so it's everything 192.168.1, 0 through 255. The next network, 192.168.2, would be in another VLAN, a VLAN 2, let's say, and you go from there. But I've walked into situations where it's like, we ran out of IP addresses, so we just added a new block, but it's all in the same VLAN. And that gets It's a mess. Yeah, it's a mess. This you can actually do this kind of stuff, but you end up sharing. It's not good. It's a bad thing, is what I'm saying. You can do it, things will work. It doesn't scale at all well. You can have security problems significantly, and so on. But that's a flat network. I don't know if you get into looking at what your customers have. Do you run into flat networks very often?
Haven't run into I don't think I've run into any flat networks actually. I think mostly because I'm dealing with bigger enterprises, so most of them have, I don't want to say complex, but more complex than that. But I try to get topologies from customers so that I can visualize and understand what their connectivity looks like.
You know how I was describing way back in our early recordings? Most networks are really a bunch of different little networks that are plugged in together. You could say that a larger network is a collection of flat networks that are interconnected. That's it. There are ways that people would argue with me about that, but you could say that that's a thing. This flat network is connected to this one, which is connected to this one, and so on. You could think of a single VLAN as a flat network, because it's a broadcast domain. It's an Ethernet broadcast domain. Yeah, you're right. I mean, what you've observed is what I have seen as well. You pretty rarely run into a flat network. If it's a network of any size, it's been broken up into multiple segments. It's got routers that are interconnecting those segments, but each of those, again, segments you might think of as a flat network all by itself. That's been interconnected. So anyway, hope I'm not twisting anybody's brain here.
I don't know about this whole networks interconnected are just flat networks interconnected, because you might have multiple not flat networks that are interconnected.
I know. I know. I said I was stretching it. I know. I know. It's just making a point. It's a way to think about it. Well, okay. So a network model, then, if we move from flat networks, another enterprise kind of local area network you probably run into is organized as a hierarchical network, I'm guessing. You've probably seen networks like this. They probably got 3 layers. There's an access layer where everybody plugs into, where your access points or your wireless access points are. You've got maybe a middle tier that would be called either the aggregation or distribution layer, and then a central layer that it would be your core layer. And this was popularized by Cisco. This is a very commonly deployed network topology that you'll find in enterprises. Have you seen networks like this?
This is what I deal with. Not necessarily all 3 tiers, but some combination.
Yeah, I agree with that too. Sometimes you won't have that middle layer, that aggregation distribution layer, because that helps you scale, but you don't need that layer depending. And in fact, trying to think, most shops that I've worked in, I don't think we ever did an aggregation distribution layer in the middle. We did access and core.
Yeah.
So all the access switches would be multi-home to a core. The core network would usually be 2 big chassis switches interconnected in some way with lots and lots of ports feeding stacks of switches that were out in the closets, and things like wireless LAN controllers and so on. Everything went from the access layer, hit the core switches, and was routed to wherever else in the network it needed to go. Because that made sense for our traffic flows. Typically, everything was in a big computer room or a small data center that those core network switches were feeding as well. And so people that were trying to hit resources in the computer room, why put them through the aggregation layer? It wasn't like, well, there's a middle tier and we don't need to bother the core with this data. We're going to just have them hit the aggregation distribution layer, and then skip over to somewhere else and go back up to the access layer. There wasn't any need like that where we wanted that middle tier in there. Or we didn't have multiple cores either. That's a scenario you can run into in some. And one shop I did, we had multiple cores because we had several different networks that were interconnecting, and we interconnected the cores together via a custom security configuration.
What is a specific use case that would require this aggregation or distribution layer?
Depending on your traffic patterns, you may want traffic to go through that middle layer and back up to the access layer. You may want to put traffic inspection in that middle layer. So you might want to have a middle layer that will collect access traffic, run it through some middle boxes for inspection security purposes. It may be that you're trying to scale to a certain size and you don't have enough port density, at the core layer to handle all of that. So you're interconnecting lots and lots of access switches into the middle layer, and then the middle layer will then not need as many uplink ports into the core layer. So it's a way you can get higher port density at the access layer out the door, and support that without having to have the core switches be so big.
Yeah.
Because you do end up in that scenario. There's also a redundancy you get, some resiliency you can get if you have two access switches in the closet that are multi-home to two aggregation switches in the middle that are multi-home to two core switches. You get a bit more redundancy there. If any one of the switches fail in that chain, you should still be okay. I mean, maybe depending on who's plugging into what at the access layer, because a lot of times that's where your single point of failure will be your uplink to the access layer.
Mm-hmm.
If it's like someone's desk in a cubicle, you're not going to multi-home that probably. But you might do something like have multiple wireless access points that are feeding the cubicle land. And one's plugged into one switch in the closet, one's plugged into another switch in the closet. Multi-home those to the two switches at your aggregation layer that are multi-home to down to the core. So you get redundancy there. And again, some people do like to use that aggregation layer like for control. I want to limit at the aggregation layer what traffic coming into the aggregation layer can get to elsewhere. And so my accounting department's coming into the aggregation layer and it can't talk to people in R&D because reasons, whatever your internal policies are, and you decide you do your traffic enforcement there at that layer rather than having all of that functionality be in the core. Because if you try to do all that stuff in the core, which you can, you end up with a really complex configuration. And so you can shift some of the security enforcement off to that middle layer and leave your core switches simple. It's nice to have a core switch that's got lots and lots of ports and just have it do one thing well. Be fast, just move traffic around. And I don't want to have this complicated troubleshooting scenario because I've got this big old core switch with a bunch of blades in it and hundreds of ports and have to think about what is that access list doing again? That's right. We were filtering between departments, and etc. So it depends, Holly.
Yeah.
Yeah. But that's why you can pick and choose. But I think to me, scale is probably the bigger driver, and then just containerizing the complexity of what security and traffic forwarding rules you might be putting in place. You might want to do that at that middle layer and let the core be the core. Don't ask the core to do too much. It's like, just route, move packets around, do it fast. And so you look at the configuration on it, and all it is just a bunch of interfaces and some routing paradigms. That's all you got to deal with. All right, so flat networks, hierarchical. Now here's a topology I know from what you've told me you do sell a bit of, and that's getting into the world of data centers. And when you're working on a data center sale, what kind of topology are you typically working with?
So that's where you've got your usually leaf spine topology. There's different variations of it, but that's probably the simplest one.
Yeah, leaf spine is super common nowadays, super popular in data centers of all kinds. They're also known as a Clos fabric, CLOS. It's named after a human being who designed this topology back in the day for other purposes. Wasn't like a modern thing that happened in the the 90s or the aughts. This was back. Gosh, I didn't look this up. The 50s, I think. Oh boy, Clos fabrics and Clos topologies solve lots of engineering sorts of problems in lots of worlds and ways. And we just happen to be applying it in this case to a what we call a leaf spine topology. So, all right, you've worked with some leaf spine topologies. Give us talk us through what does the traffic flow look like in a 3-stage leaf spine topology? I'll just give it a shot. Come on.
See, this goes back to my question before we started recording this. If you look at a leaf spine and you look at like an access core, take away what they do and just look at it on paper. You've got, different switches, they're interconnected, and there's 2 tiers, and they look the same.
They look similar. They are not the same. And this is why I want you to walk through the 3-stage traffic flow. That's data center to data center. Let's just focus on that. It's the traffic flows. You're those east-west flows between one host in a data center to another host in a data center via the leaf spine. What would that look like? Just walk us through the switches that it's going to hop through.
Well, so this is all kind of dependent on how you've configured and what protocols you're using. But in theory, what you're doing is usually you might have a spine. For the listeners, I've got a very visual describer, so you can go watch the YouTube and see.
She's waving her hands all around, yeah.
But you've got the leaves, and what's going to happen is if you need leaf-to-leaf communication, you want to send packets from one leaf to another, it's going to be sent through the spine. So it's like does a loop from leaf to spine, depending if there's another layer, it could go depending on what you're doing.
3-stage, we're just going to keep it simple.
Yeah, leaf, spine, and back to the leaf. So you don't have direct communication from leaf to leaf usually. You can, but you shouldn't. So that's at base level what it looks like, where I guess if you're doing access versus core, like if we compare it there, usually access, you've got, this is me speaking through this in my own brain to figure this out, but you've got hosts connect to the access layer. You don't need to go through the core for different hosts plugged into your access layer to send packets between one another, right?
No, you don't. You're right.
Yeah. Then conversely, when you're dealing with this Clos fabric, you do it differently. It's leaf to spine, but it's going to be routed through that fabric.
Okay. So I thank you for suffering through that. I made you. She did not know I was going to do that to her and make her go through that thought exercise. But all right. So let's back up a second and talk about leaf spine. So in a simple leaf spine topology, the intention of that network topology is to have very predictable network forwarding characteristics, behavior, as the packets flow from host to host within that data center. When we say leaf, we're talking about a top-of-rack switch, a switch that is where your hosts plug in, your servers in the data center probably plugging in to a leaf switch. That leaf switch is connected to a spine switch, like the backbone. Think of it as the backbone. And then it is going to be communicating to another host that's hanging off of a different leaf switch, presumably. And all of the host communications in the data center then are flowing into a leaf, through a spine, back out to a leaf, to the receiving host. I say predictable behavior because every host in the data center is plugged in so that you know exactly how much latency you're going to have to get from leaf to spine to leaf. And in that way, you know, based on your traffic patterns and your traffic load, like you're running a very specific kind of database or you're doing very specific kind of computation. And you know you can count on the network to deliver packets from host to host in that predictable latency profile, because it's always the same. It's never like it's going to go from this switch, then it might go to 2 other ones, then it's going to go over here, and then it's going to go. But if it's this other host, the way we cabled those guys up, they're going to be like direct. And so the latency profile is different. No. Always the same. Everything's going to be the same. It's going to be predictable. And as you pointed out when you were describing 3-stage leaf spine, you do not have leaves plugged into each other. That's not a thing. You don't have, if you've got a row of top of rack switches, like you said, You can, people do it occasionally because reasons, but you shouldn't do that.
Yeah.
That is not the intended design of a leaf spine 3-stage network.
I think one thing to point out that confused me initially when I first heard about 3-stage was what it's called. Because in my brain, I don't want to confuse people by saying this, but I think 3 stages and I think 3 tiers. And that's not what 3-stage means.
Right.
That's referring to the flow of traffic, how, leaf, spine, leaf, those are your 3 stages from where it's being sent to where the packet's being received. And that's important because I think visually my brain likes to confuse that for some reason.
So there's another element to add now to this 3-stage fabric, to this leaf spine architecture, which is ECMP, equal cost multipath. Multi-homing, that is, the leaf switch or a leaf switch is going to be connected to 2 or more spine switches. And then traffic using an algorithm will be distributed across those different leaf to spine uplinks. You get redundancy out of that. So if you lose a spine switch, you're still able to forward in that predictable way. And you also get capacity, so that the bigger you make the interconnection between the leaf layer and the spine layer, the more traffic that you're able to carry from your servers that are flowing into the access switches. So one thing that comes up within the discussion of leaf spine topologies is, what is my oversubscription ratio? Have you run into this in some of your discussions?
Yeah, I have. Don't ask me to explain it, but I have.
Okay.
But I know that there's a calculation, and obviously it's to work out your redundancy and how many extra ports you would want in case something goes wrong.
So redundancy is definitely part of it. Performance is another part of it too. So here's what's going on. Here's the thing. Let's come up with a simple example of you've got a 48 port 10 gig switch. So there's 48 server facing ports. The ports you're going to plug your servers into, and they're 10 gig. We'll just for the sake of math, we're going to keep it simple. Okay, so that means we could have as many as 480 gigabits per second of traffic flowing, at least in one direction, coming into that switch. If every server connected to that switch was talking at full line rate, that'd be 480 gigabits per second flowing into that switch. Well, where's it going? It's going down to the spine layer, right? So the next question then, and then where we get into this oversubscription thing, is, well, how much bandwidth is connecting that leaf switch into the spine layer? If we wanted to carry every packet and not drop any packets, we need to have at least 480 gigabits per second flowing from that switch down into the spine. But usually you don't have that situation, right? Where everybody on the switch is talking at full line rate. That doesn't happen. You don't really need 480 gigabits per second, right? Because most typical traffic patterns are kind of bursty. I'm talking loud right now, and no, I'm not going to say anything. And so you end up with these traffic patterns that are, kind of spiky. So you don't need to have necessarily 480 gigabits per second flowing down into the spine layer. Your uplink ports, and let's say on this particular switch, it's 100 gigabit per second uplink ports. So you might have 48 of those 10 gig ports facing the servers, and then 400 gig ports facing the spine. That would give us 400 gigabits per second flowing from that access switch, or from the leaf switch down into the spine switch. So I got 480 potentially that could flow in, and 400 that could flow out. So my oversubscription ratio is math, whatever 480 divided by 400 is, 1 point something. It's a number. The lower now, but what's the trade-off? So you as a salesperson know that the trade-off is going to be budget, because 100 gig ports cost money. And that means, depending on how you're designing this thing, your oversubscription ratio will drive how many spine ports you got to have with, in my example, 100 gig ports in it. And 100 gig ports have come down a lot over the years, but they still ain't free. And so you got to decide, well, can I get away with 2 uplink ports? Would that be enough? 1 port to one spine switch, another 100 gig port to a second spine switch. Would that be good enough? changes my oversubscription ratio. But if it's, enough, if 200 gigabits per second is enough to handle the 480 potential coming in, maybe I'll do that and save some money. I still get good, I'm not going to create too many congestion points, or I'm not going to create congestion too often, then I'm okay. All right. Did that help put anything together for you from some of the sales exercises you've been working through?
It does. I do have a lingering question, and I don't want to necessarily go down this rabbit hole, but for my own personal...
But you're jumping in anyway. I can see this happening right now.
I need it. Because I understand what, where my confusion around these topologies lies. And it's because typically you think about these three-stage fabrics, or you think about Clos fabrics as data center. You think about access aggregation core as enterprise lands. They're quite separate. I now work in a space where I'm doing Clos fabrics in enterprises, and we just call them campus fabrics. But now in theory, it's a data center centric design or topology, but your leafs, what's plugging into those leafs isn't typically what you would see plugging into a leaf in a Clos fabric. So now I'm stuck in a space where, yes, it's a kind of a leaf spine, leaf topology, but we're not really using the correct terminology because it's not in a data center. So now we're conflating the word leaf with access, and because, we've got access points plugging into technically leafs. And it gets messy. And I don't know if it's just people conflating terminology, because semantics, the network's going to do what the network's going to do regardless of what you call it. But then I come in and I'm like, okay, but is it an access? Is it a leaf? I know we're doing Clos fabrics, but why are we not using that terminology then? And that's when I get confused. So I don't know what my question is. My question is why? What's going on?
What's happened over the last...
Can people use the correct words?
5 years or so is leaf spine has started to become the reference architecture that a lot of networking vendors are putting out for everywhere. And so that's what you're experiencing. You're running into that, where previously leaf spine was like, oh, that's a data center thing. And, we don't do that in the enterprise. And all of a sudden it's like, actually, leaf spine's got so much to commend it. I think we can use this in the enterprise, and you can. You can. There's nothing stopping you from doing that. Just like there's nothing stopping you from using MPLS, which a lot of people think of as a service provider way to do transport, and using it in enterprise. You can, and enterprises do. They do use MPLS. Just because you think of it or put it in a certain bucket doesn't mean that technology is not usable in other contexts. And you're living with this, you're seeing this. And so it kind of does become a game of, well, what do words mean? Well, yeah, I mean, from a campus fabric design perspective, do we think of the leaf layer as leaves, even though that's how we're connecting them and that's how they're functioning, and we're delivering a 3-stage leaf spine Clos fabric to the campus? Why did we call it the access layer? Because that's what people are used to. They're used to calling it an access layer. They didn't, data center fabrics and leaf spine weren't popular, I would say, until 10 to 15 years ago. They became to be like, yeah, this is kind of the way we're going to do everything. And slowly but surely, you started seeing the vendor validated designs. That's a key term. If you look for validated designs, that means something in vendor land, where they've produced with certain versions of their software, certain ways the routing protocols were designed, and so on, the way the physical architecture is. This is a reference you can emulate at your company, and we know this is going to work because we tested it to death. And look, here's the gargantuan PDF that shows that. Wait, we can apply this to campuses as well. This whole leaf spine thing we've been doing in the data center for a while simplifies the number of validated reference designs we've got out there, allows us to make the network a bit more modular. We can plug in the system here, and this other solution that we're selling would fit in there pretty well without the customer having to redesign their whole network. And then Holly finds herself in the middle of this, where, why aren't we calling it a leaf? It's a leaf. Because leaf implies, to me anyway, it implies data center fabric. And data center people that are in data center design and are designing a data center specifically to deliver some kind of a computing platform are thinking leaf spine. They're thinking, I'm going to dual home my server to 2 top of rack switches, and get that full redundancy and get the performance characteristics I'm looking for. I have an application that is running across in a distributed fashion across lots and lots of servers and lots of racks, and I need to know, no matter where I put the workload in this distributed software, that it's going to behave in the same way. And so again, leaf and spine from a network perspective means something to them, because they know that means I'm going to deliver this very predictable network performance characteristic. And so applying that to campus, I mean, well, again, what do words mean? Whereas some people are going to get very upset if you do something like interconnect 2 leaves in a data center,
Yeah.
Or 2 spines in a data center. They'll be very upset if you do that. You're not supposed to do that either. The only connections between leaves and spines are supposed to be between the leaves and the spines, not leaf to leaf, not spine to spine. You might get away with that, or there might be better reasons to have an exception to the rule in campus design. Because campus buildings are weird, and you're dealing with fiber running in a tunnel underground this one way because that's what you've got. And the way the Wi-Fi works requires whatever. And your traffic patterns between this group and between R&D and Q&A and so on might require something where it'd be a lot more efficient if this part of the network never saw that traffic. But if we stick with leaf spine, it's going to see that traffic. But that's dumb. Why are we doing that? Let's do a home run between here and here. And I think, to me, it would be more forgivable because you're working within the physical constraints of a campus and how weird it can be.
Yeah.
And not saying, no, it shall only be leaf spine like in the data center, and it shall not change. You're not... I don't know. That's just my opinion. Other people may have different takes on it. That didn't help at all, though, did it? I don't know.
No, it definitely did, because I think you're dealing with 2 types of network engineers, where campus, they've designed very specific topologies and they've been calling them access and core and everything else for forever. Just because they're implementing a new topology doesn't mean they're going to change their lingo, even if technically speaking, it's not correct to the topology. Nobody actually uses the word frames day to day.
Right. No,
they just say
right.
packets. Yeah. And I think that's the same thing here. And if you are new, and when I started this and I'm like, okay, campus, fabrics, access, core, whatever, but it's leaf spine, and now I'm thinking, well, it's just the same thing. They're all the same. It's an access, it's a leaf, things plug into it, but it's not the same. And I think I'm not going to be that person that jumps on a call and a customer's like, oh yeah, my access switch. I'm like, actually, it's a leaf. Please use the correct.
Actually, yeah.
I'm not going to do that. But it helps in my own head to remind myself that, like, no, it's not an access, or like, this is not the core, this is the spine, because that's important for like the traffic flow and what we're doing with the whole topology. And I would like it if people were more specific, just to confuse me less. But each to their own.
Well, right. I mean, in the way, if you look at the configuration of a leaf and a spine switch, they're going to be very different. And I know you've run into some of this too, dealing with EVPN. Like the spine switch is pretty simple compared to a leaf switch. There's no VTEP on a spine switch, right? Correct me if I'm wrong, but you got your VTEPs are leaf to leaf. And so you end up with a simpler spine switch.
Yes.
Yes, she says uncertain.
No, because I'm just thinking. I'm thinking about the difference between it. We do not have to discuss this here, but the difference between ERB and CRB and edge router bridging, and that's going to depend where your VTEPs are. But yes, in theory, your VTEPs are on your leaf switch, which you're not going to have in on your access switch. I mean, you won't even think about VTEPs if you have an access core deployment.
Right. Yes, unless you've deployed, EVPN for whatever your reason is, and I know there are campus fabrics that do use EVPN.
And then they are technically not in an access core topology, but yes.
Oh, you got your "Well, actually" T-shirt on.
Well, that's what I see. It's exactly that. It's, oh, we want to do EVP and VXLAN. That's the use case. So we just do it in a Clos fabric because that makes sense. Or very specific collapse core, multi-homing, whatever. We don't have to discuss it. But it's when do we start calling them leaves and spines versus access and cores? What is that? What's the change? Where, and it's not because it's in a data center. And I'm sorry, I've gone down a very long rabbit hole, and
No,
I knew we were going here, but like, it's something that I think it's something I deal with nearly every day.
Yeah.
So it's top of mind.
Well, okay. So this whole rabbit hole we jumped down, we got there from the platform of three-stage leaf to spine to leaf, 1, 2, 3 of Clos fabrics. Well, there's also 5-stage and 7-stage, and we don't need to elaborate on those much more than just to say this is about scaling. How many access ports do you need to support in your fabric? If you get really big, it could be that 3-stage doesn't give you as many access ports as you need because you need many thousands of them. Well, in that case, you move to a 5-stage fabric, which would be leaf to spine to super spine to back to another spine and then back to your leaf again. So 5 stages. If you need to go even, and that gives you more scale. Now you can support more access switches, more leaves. Well, actually, leaves still have access ports. They do. They may not call them access switches, but they do have access ports. Yes. If you need to go even bigger than 5-stage, you can go to 7-stage, leaf, spine, super spine, and then a core layer, or sometimes people call them an ultra or a mega spine, to a super spine, to, I'm losing count, to a spine, to a leaf again. And then all of this just has to do with, again, how wide of a leaf layer do you need? How many thousands of ports do you need to support in a single fabric? When does it make sense to have multiple 3-stage fabrics as opposed to expanding to a 5-stage or a 7-stage fabric? And those are questions that have that network architects with lots and lots of experience who have a deep understanding of what you're trying to accomplish in the data center, what your traffic flows are like, how your compute needs to work, would be able to answer that question. These are elaborate cabling exercises with a great deal of complexity, typically running in data centers that are absolutely massive, supporting operations like you're a cloud service provider at Amazon, or you're LinkedIn, let's say, and you need to run a gargantuan fabrics. You'll go from 3 to a 5 or perhaps a 7 stage fabric. I'm saying just to let people know that this exists. All right, so one more point about leaf spine fabrics, because I don't know what it is. We got to stop saying before the show, this won't take long to record, and then we're hammering on an hour here, and we still got all this other stuff to talk about. But in a leaf spine fabric, how do you get out of the thing? How do you interconnect that network, that leaf spine environment, to the rest of the world? Well, they have something called border or edge leaves to connect outside the fabric, where you've got some switches that are dedicated to interconnecting that whole fabric to some other part of the network. I assume that's a standard part of leaf spine design in your world?
You come across it.
Yeah. Yeah, you're some kind of an edge connection, because you got to get to the internet somehow. You gotta, and there are different ways to do it. The typical way I've seen it done, not the only way it could be done, certainly, but you've got a couple of leaf switches that are dedicated to that being the edge of that fabric and getting you connected to the rest of your network, to other networks out there. They're custom purposed for the role. So there's some other data center terms, and there's many other options aside from leaf spine. Super common to have leaf spine out there, but you might run into something called a butterfly network. You might see something called a torus or a hypercube. We're not talking about these at all. They're super interesting and cool and have their use cases. A lot of them have to do with, I want to have as many hosts directly connect to each other, one-to-one, directly connected, no spine layer, as possible. And so you might use a torus or a hypercube for that, or you're looking for very specific forwarding characteristics. I think of these more as special use case corner cases, not nearly as common. If you run into a network that was designed as a hypercube, you want to sit with the designer and go, oh, why? Tell me this story. I want to learn something. This ought to be cool. Because, yeah, I've never worked in that environment. I have had that conversation. There are some circumstances that I understand where a torus or a hypercube might fit to help facilitate those one-to-one connections. But it's beyond the scope of our conversation today. But if you're listening to this and you want to see some cool stuff, go Google those words like hypercube network architecture and see what comes up and start looking at the diagrams. It's like super fun, really interesting stuff. Oh man, we're at 40 minutes, Holly. Okay, let's see what we can. Let's hammer through some more terms. Let's do this. Let's keep going. All right. So enterprise WANs have some common terminology as well that you'll see describing certain network topologies. One is very simple, the point-to-point network. And what do you suppose that's about, Holly?
When one point is connected directly to another point.
Just like it sounds. Yeah, not too complicated.
I like these terms.
not hard at all. Yeah, but you hear it is as intuitive as it sounds. A point-to-point network. You're connecting 2 points directly to one another. Very commonly used in wide area networks to connect, say, a remote office to a different remote office. They'll be done via some kind of a point-to-point link. You could describe any single point that connects to another point as a point-to-point link, for sure. You'll see that come up in training material and just generally referred to things. All right, moving on from point to point then. In an enterprise wide area network, a WAN, you might also have a hub and spoke topology. And what's that bring to mind for you?
So what does it bring to mind? Tires and but no, you've got a central hub, so there's that center, and then you've got, as it sounds, you've got other WANs that are connecting all back to that central hub. So those spokes are now all connecting back to one central location, one central WAN. So in theory, you could think of it as multiple point-to-points back to one.
Yeah, that's a very fair way to put it.
Hub.
And I think the key aspect of a hub and spoke topology is that you must route through the hub to talk to another spoke. So if you're spoke A and you want to talk to spoke B, you got to go through the hub for that traffic to get there. And people will design networks in this way very often for security reasons. I want the hub to enforce a certain security policy, and so I must push traffic into the hub so that whatever the enforcement device is, probably a firewall, could be a complex stack of security devices, can enforce that policy. Traffic flows in from the spoke to the hub. The hub does the traffic inspection. Everything's good, or it's not good, as the case may be. Maybe it drops it, or everyththing's great, and it forwards it to the other spoke, and everything is handled that way. What would you think of hub and spoke topology? What would you imagine is a design drawback of that?
Well, it means that every spoke that wants to communicate with any other spoke has to go through the hub. So there's definitely, depending on what your goal is, but there's going to be maybe some latency, or if every spoke is talking to every other spoke at the exact same time, which is very unlikely, you're relying on just the hub to push all that traffic out.
Yeah, so latency is definitely a potential concern, because you're adding the latency of the full length of spoke to hub and then hub back to spoke. So you have to add up those two circuits, whatever the latency is there. And the hub is a potential bottleneck, as you were saying. What if everybody's talking at once? What if there's a ton of traffic flowing through the firewall that you're asking to do security enforcement, and that thing's starting to get hammered because of all the traffic that you've insisted flow through it for inspections? So it could be a potential bottleneck there. Which takes us to the next topology, which is a mesh. What do you think a mesh is?
So depending on how you set it up, but a mesh is where everything is interconnected. So you don't want to have this hub and spoke or point to point. Well, point to point, I'll leave that out of this conversation. But like everything, you want to be able to communicate with everything else without having to be sent through a specific location or WAN or router. So A can talk to B, which can talk to C, which can talk to D, and maybe you want everything interconnected.
Yeah, and the way these are typically done these days, you don't have multiple physical circuits that are connecting all these sites to one another. In a modern sense, if you have a full mesh, like you were just describing, A can talk to B, can talk to C, can talk, etc., you probably have an overlay involved in some way. For example, software-defined WAN, which we've talked about in previous episodes, at least at a high level, how that would work. You have maybe one link coming from site A into the internet, but then there's multiple tunnels that go from site A to site B, site A to site C, site A to site D, etc. And so you end up with this mesh-like configuration of tunnels that are overlaid on top of the physical connections, and that gives you that mesh topology. Now we're talking full mesh in this case, and what can get weird about this is what happens if you're building, well, let's just stick with the software-defined WAN example, and you've got 100 sites. Well, let's back up. What if you got 3 sites? Okay, you got a pretty limited number of tunnels, but everybody can talk to everybody with a tunnel directly. All right, let's bump that up to 10 sites. Okay, that means every endpoint, every SD-WAN router now has 9 tunnels from itself to everybody else, times 10 sites. So you end up with, what is that, 90 tunnels, something like that? There's a formula for this, 90, whatever the math works out to. There's an n+1 divided by formula that I don't have off the top of my head. You know this formula? You've seen this? Yeah.
Yes.
Okay, what if you got 100 sites? What if you got 500 sites? Or how many tunnels do you want to do? It's hard to do tunnels because you have the router's got to do math, it's got to do cryptography, it's doing authentication so that you know that the tunnels are allowed and you're talking to who you think you're talking to. There's a lot going on. So there's a scaling problem there. So what you might do is not a full mesh in your software-defined WAN. You might do a partial mesh, which is for the most part, the endpoints don't need to talk to each other, but they do need to talk to these, 10 different sites. We got our 3 data centers, and then there are these 7 crucial business partners that we work with. And so we're going to set up a mesh that isn't everybody to everybody. It's everybody to certain people, certain endpoints that we can talk to. And so you end up with a partial mesh topology that you can design within your software-defined WAN user interface and make that happen. So full mesh, partial mesh. Those are very common things. All right, and that's enterprise WANs. Now, to close this episode out, Holly, that that somehow we're going to hit an hour again, or almost, I wanted to throw out some other network topology terms, just kind of quickly defining them because you run into them, especially when you're designing WANs or you're shopping for a service provider WAN or you're reading about how a company does something. A lot of these terms come up in the context of like the broader internet, great big service provider networks that are distributed globally. There's a lot of terms that pop up. And so let's walk through them. The first one is last mile. When you're talking about a service provider network and you hear the term last mile, does that mean anything to you?
It only means something to me because you've mentioned it in a couple episodes, actually. And I think it is what it sounds like. It's how is that traffic, or what does it look like to get to your house? Or not your house, your whatever. Your network. Your house,
your business, right. It's the final connection to the physical premises.
Yeah.
You gotta have wire, or you gotta have a wireless connection off a tower somewhere. It's the last mile. It's the last piece of it, which from a service provider perspective is an interesting challenge because in America, anyway, in the US, the last mile is governed by a whole bunch of different providers. There's a hodgepodge of different companies that can deliver last mile services to you. In my neighborhood, which is the rural mountains of northern New Hampshire, there's at least two different last mile providers. I know one is the local cable company. They've got a last mile coaxial cabling infrastructure. And then there's a new provider that came in within the last year that's providing fiber. They strung new fiber on the poles that can also provide last mile. And there may be some more. And then it's the same. Like you live in a densely populated city area.
Yeah.
You probably got lots of last mile providers, I'm guessing, because service providers love to provide last mile where they know they can make money. And where can they make money? Where there's people and businesses and buildings and so on. Not where I live, because there's trees out that window, not more buildings. So that's last mile. That's what we're talking about. Middle mile. Have you heard the term middle mile?
Again, I think you've mentioned it at some point, but not as frequently as last mile's been discussed.
Well, it's what's implied. It's the different carriers that provide connectivity from different regional networks. There's that middle mile. How am I getting traffic from where I am across to this region that I want to serve? And you can buy passage, if you will, along the middle mile. Basically, get some bandwidth of your own, through that with different providers that'll provide you traffic across that middle mile. And then if you realize we're going through tiers here, there's something called a tier 1 network. If you hear of a tier 1 network, what's that mean?
I've, again, heard the term, like the service provider space is not where I play. So
tier 1, these are the companies, I would say, that make up the backbone of the internet. It's like you can think of it like they are the internet and they interconnect with each other. And a lot of them have really interesting histories that go back to the 70s, 80s, 90s when the global internet was being built out. A tier 1 provider I'm hierarchically not a leaf hanging off of a branch. I am the branch, or I'm the trunk of the tree, really, if you want to think about it using a tree analogy, would be a tier 1 network. I think of providers like in America, Verizon's got a lot of tier 1. There's been so many acquisitions and mergers that I've really lost track of who owns who anymore. But back in the day, there was a company called BBN Planet. I know they're long gone from an individual perspective, but the network still exists. They're a tier 1 provider. Level 3 was a tier 1 provider back in the day. AT&T would be a global tier 1 provider. You can look at a lot of the cloud service providers now, I think, as providing, if not internet tier 1 services. Certainly you could think of them as a tier 1 class carrier because they have a global network and they own much of their own infrastructure, if not all of it. Like Google, Microsoft, and Amazon have absolutely massive global networks with fiber that they own. Meta, Facebook, and so on. They've got tons of their own fiber. I think you could categorize them as a tier 1 network from a certain point of view. They may be prioritizing traffic for their own services, but they are also, in many cases, they are carrying traffic for other providers as well, depending on who they are and what their business model is. Like, I don't have any idea if Meta carries non-Meta traffic for whatever their reasons might be, but I know Google does. For example, they just announced, hey, you can use us as a backbone provider, basically, for your wide area network globally if you want. Okay, as we're getting towards the end of this show here, let's give a few more terms. Internet exchange points. Another term you've heard of, maybe? IXPs?
No, actually.
Okay, this is an interesting one. IXPs are super cool. Like, if I could have like my dream job, it would be working in an IXP. That would be fun for me. What it is I'm going to oversimplify this, and people that run IXPs are going to tell me things, but I think of it as like a bunch of routers, sitting in a rack with a bunch of fiber coming in from a bunch of different providers, and you're interconnecting that fiber into those routers and then negotiating very particular relationships. I want traffic from my business that's in this region that does a lot of business with this other big company in my region to connect directly. And I don't want to have to do it over the internet because latency and so on is very important to me. Bandwidth is very important to me. I'm going to contract with an IXP, an internet exchange point, so that my business and this other business I want to do business with and have very close data connections to, we're going to connect in the middle at this IXP and have a direct connection one to another, a very efficient connection one to another. And there's a lot of different companies that might like to use IXPs. Google, as I understand, was huge, connecting with different IXPs all over the world, so that when you type in google.com to do a Google search, or you use 8.8.8.8 as your DNS server, you're very close to it. So an internet exchange point helps provide services and makes them very close to you no matter where you are, rather than you having to connect up through to a tier 1 provider and then back down to wherever the resource is that you're trying to connect to. Now you've got this bang, this it's like a shortcut, if you will.
Yeah.
It's adding more complexity to the mesh that is the internet. I don't mean complexity in a bad way. I just mean, like, if you look at the spider web of how the internet is connected to each other, internet exchange points just provide another place to plug in and connect to different resources. Where they are regionally, where all the fiber is in your region, can make someone much closer to you in a latency standpoint than otherwise you might have. Other example of someone that might use an IXP might be Netflix. Might be our next term, actually, a content delivery network. When you fire up the Netflix app and you want to see the content and then watch a show or see a movie, what's happening? Are you talking to a giant Netflix server that lives in the heartland of America somewhere? No, you're talking to some stack of boxes that has tons and tons of storage on it, that's got a copy of the thing you want to watch sitting on it. And through the magic of internet exchange points and Netflix's content delivery network, it's going to serve up a copy of the movie that's closest to you. I have no idea how big Netflix's network is. They have an engineering blog where they talk about this kind of stuff. But there's copies of their content scattered all over the world in different repositories with, it's actually not as big as you'd think. It's not like it's got to be like 100 racks to have a copy of the Netflix catalog nearby. No, actually it isn't. To have a Netflix node is it's not that big of a server, as I recall. Anyway, the way they get that done is plugging in a box, maybe to an internet exchange point from their own content delivery network. And then there's CDNs all over the world, content delivery networks that are delivering different sorts of content. Having a copy of the content you want to see stashed in regions all over the world, so that no matter where you are, from a latency perspective, there's some copy of it that's going to be close to you and it and delivers to you. Have you heard of CDNs? Was that a term you'd run into before?
No. These are all new terms for me. That's super interesting, though.
More cool tech. And you being at Juniper, I mean, Juniper is big in the service provider space, and and it has CDN customers for sure. So I mean, if you poke around at the right people within Juniper, there's going to be some people that know a lot about CDNs and internet exchange points, and it'll be like, that Banks you were talking to, he sort of knew what he was talking about. Let me show you what's really up, Holly. So there's people to go after.
I've got to go chat to the service provider org.
Oh yeah. There's some incredibly knowledgeable people in that group. I've talked to a few of them over the years. Really interesting stories, networks, and problems that they're trying to solve at global scale. Super cool stuff. A couple more terms before we call it. Eyeball networks. Have you heard of eyeball networks? No?
No.
What do you think it is? Take a guess.
An eyeball network?
Mm-hmm.
I don't know. I guess it's something that really sees everything. Yeah.
So an eyeball network is it's kind of like the last mile network. It's the network that is delivering content to someone's eyeballs. So Netflix cares about this in the sense that what's the quality of the last mile that we're delivering our data stream to, so that someone can watch a video. That's the eyeball network. In my case, the eyeball network would be the fiber network that I have connected my house to, so that when I'm watching Netflix, it's I think the easiest way to describe it is it's just another way to describe last mile. But the context is usually there is someone watching the content that is being delivered via that network, the eyeball network. And so that'll come up in certain architecture conversations as jargon.
Yeah.
And then the last one, our last term for today, is edge network. Maybe you've run into this one. I know we've talked a little bit about it in some other shows.
I don't know if I've run into, I mean, I know this is under like the service provider context. So like you get edge networks on a smaller scale. So I don't know if, I mean, I guess an edge network is what it sounds like. It's the network on the edge that's connecting other networks usually.
Yeah. An edge network will often exist because there's data processing that has to happen, and maybe ordinarily you would have sent that data up to the cloud, Amazon or whoever, to do the processing. But in this case, if you do that, the processing is going to take too long. Too much latency would be introduced into the computing transaction. And so you keep it local, and you attach the local servers that are going to do that compute on the edge network. An example of an edge network might be industrial applications. You're an oil platform, and you've got lots of data processing you're doing as you are processing, doing oil processing, pulling oil out of the ground and so on. And you can't wait for the cloud to do that because you're in the middle of the ocean and your connectivity to the cloud kind of sucks. And so how do you do it? You do that processing locally. Factory automation is another use case I've heard where it could be the decisions you have to make in that factory need sub-millisecond response time, and you can't ship it up to the cloud, wait for that computation, ship it back down, and then go. Too many milliseconds for that to happen. So you build an edge network where it's the edge network is you to get that stuff done, get that compute done. Whoo! Okay,
our short episode for today.
They're getting. These shows are getting ridiculously long, Holly. Okay. All right. Before we close this off, you got any final questions or comments on all of this?
I think I've learned and heard of a lot of new cool jargon, which I think as long as you're in the industry, you're always going to have something new to learn. So I'm excited to go and dive into some of these. And the content delivery network is definitely quite an interesting topic.
It's so interesting. Yeah. Akamai, AKA-MAI, is a company that you might want to poke around at. I think they're somewhat public about how they do what they do. They're a very well recognized global CDN brand, but there's a bunch of them out there. Just dig into that. Super fun, super interesting what they do and how they do what they do. Well, okay, everybody, you've killed an hour with Holly and I again. Thank you for listening to NS for Networking today. If you have questions, comments, or requests for a future episode, something that you want us to discuss, you can do that via packetpushers.net/follow-up. And Holly and I are on LinkedIn, and we're also on the Packet Pushers community Slack group, so you can connect with us there. The Slack group is free. It's a great place to connect with other networking nerds. There's over 3,500 people in that group, and then more people join. Literally, more people join every day. And they're from all over the world, all sorts of cultures, all sorts of backgrounds. They're hanging out, they're chatting. You can learn a lot. If you want to lurk, you can participate, ask questions. Just come on in. The water's warm. packetpushers.net/community to join that Slack group. Now, if you'd like to watch Holly and I instead of just listening to us, head over to the NS for Networking podcast on the Packet Pushers YouTube channel. We're upgrading our video. Holly and I are experimenting with a new platform right now. We're working on our lighting and our cameras and all of that stuff. So hopefully it's going to look better than shot on potato. We are trying to upgrade the viewing experience if you want to watch us on YouTube. And let other people know about the show. A lot of you have emailed us and told us that you're really getting value from the show. We appreciate that. Tell your friends. That would be awesome. And last but not least, just remember that networking isn't hard. Other people figured it out, so you can too.